This video is for digital signal processing. It's for lecture 4 on Fourier transform pairs. The first question you might have is, why am I making a video on Fourier transform pairs when I haven't for other topics? The reason is that if you understand these pairs, you'll have a lot of good insight into design trade-offs. Quite often in DSP, we have some behavior we want in time, some behavior in frequency, and it's not always possible to simultaneously get both of those satisfied, so we do trade-offs, and these pairs will give you a kind of an intuition into if you change something, how is things going to change in the other domain. The key insight that we'll see is that a lot of, in all cases, a sharp transition in one domain means a gradual transition in the other domain. So for example, if we have a signal that kind of comes along, maybe it's very small, and then maybe there's a big spike, so there's a very sharp transition here, maybe like an EKG signal is an example of a sharp spike. That will tend to be something that has a lot of content across a lot of frequencies. So here, this is my frequency, and this is time. This is x of n, and this is the frequency domain x of omega. Okay. On the other hand, if I have a signal that is changing much more slowly, maybe kind of meandering around somehow, that will tend, in this case you can see this is pretty low frequency, that'll tend maybe to be pretty compact in the frequency domain. So smeared in one domain, compact in the other, and vice versa. The first examples that I want to look at are impulses in time in the first case and frequency in the second case. So I'll do some examples where here I'll have time, so sample number is n, this is time, and here I'll have frequency, omega being radian frequency. We're using here the discrete time Fourier transform, so this is the formula for it, the transform pair. To get the answer to particular omega, we basically add up all of our time samples at different samples n, weighted by an appropriate complex weighting for each n, and then omega is the same in all these. We add it up, we get the response at omega. On the other hand, to go the other way, we would say we now have an integral, because for the dt ft, time is discretized, remember, but frequency is still continuous. So we have a regular integral, continuous integral, over frequency, and we're going to add up all of the frequency components with the right phasing to give the answer at sample number n. So the simplest case we can look at here is a time impulse. So let's say, to make things simple, that this is just delta of n. There's a signal that is only non-zero at n equals 0. Now sometimes I will draw a bunch of zeros elsewhere like this that you can imagine kind of go to infinity. Sometimes I won't, I'll just draw the non-zero one, but the idea here is it's only non-zero there. Okay. So we want to transform this guy back and forth, and it turns out, if you look at this, we want to compute x of omega here, right? And this signal is only non-zero at n equals 0, so we'll have a 1 at n equals 0 and then a 0. So this is just e to the 0, or 1. So if I draw that, it's very easy to draw, except for I can't, of course, draw a straight line. This is x of omega. This basically says that if we have an impulse in time, that gives us a flat spectrum. Okay, meaning that, to recreate this signal in time, we need to add up every single frequency possible. There actually are real-world ways in which this is used. You might remember the movie Ocean's 11 or 12. There's a part of the movie where they set off an electromagnetic pulse in Las Vegas, a very strong electromagnetic signal in time, and that pulse fries all the electronics in all the casinos so they can steal everything. And the theory behind electromagnetic pulse is when you have a very strong pulse, that'll send out electromagnetic energy at all frequencies, and any electronic equipment operating at any of these frequencies will get overloaded and damaged. There was actually a big worry back in Cold War days that the Russians could do that by just blowing up a bomb in the atmosphere over the US. It would disable our military, which at that time was much more dependent on electronics than theirs, and people were kind of worried about that. But anyway, the Fourier transform pair is time, impulse, flat spectrum. Okay, so let's look at the equivalent of, we could think of this as a frequency impulse, but we can just say x of omega is delta of omega. So now we're going to go over here and we're going to say at omega equals 0, and pretend that points to 0, we have a delta function which I'll draw with this kind of double arrow here. What do we get in the time domain from that? So now we use this formula. We have an integral, a factor of 1 over 2 pi, an integral over omega, which is only non-zero at omega equal to 0, and the property of the delta function is that it pulls out the value at that point. So we can say that is going to go to x of n equal to 1 over 2 pi, there's our constant out front, times e, again, e to the 0, or just 1 over 2 pi. So we get now in time something 1 over 2 pi. And this makes sense. If you had a constant signal that never changed, you expect that that should give you a, this is a DC signal. It only has 0 frequency, so you would expect the frequency spectrum to be something like this, x of omega being a delta function. Okay, and what we can see here, there's kind of a mirror image thing going on. If we have an impulse in time, we get a constant in frequency. If we have an impulse in frequency, we get a constant in time. And the only differences are this 1 over 2 pi. Basically, depending on how you define the Fourier transform, there'll be different constants. But otherwise, the answers are kind of mirror images, time to frequency, or the same thing, similar thing in frequency going back to time. We can get one step more complicated if we consider before the impulses were always at the origin, but they don't have to be, right? So we could have, as an example, x of n equals delta n minus 4. This is kind of like the thing before, except for at n equal to 4, we have a delta function. So here's our x of n. What does that give us? Well, we plunk that into the formula here. Again, there's only one non-zero term, but now it's at n equal 4. It has value 1, because the delta function is just 1. And then, but it's n equal 4, so we get x of omega is equal to e to the minus j 4 omega times 1. So we'll put that there. Okay, so this is basically, we'll come back to this later. This is like a linear phase shift. So this is really a Fourier transform property, not really a pair. If you shift something in time, you get a phase shift on it. Okay, the other case you could say, well, what if we look now at omega, so this is going to be x of omega, and instead of having a DC, what if we had some frequency, some spike somewhere else? So maybe we have a spike over here at omega naught. So this is delta omega minus omega 0. Again, we can find x of n by putting in this formula. There's only one, the delta function pulls out the value at omega equal omega 0. It's 0 everywhere else, so we get x of n is equal to 1 over 2 pi times e to the minus j omega naught n. This is now, if we plot it in time n, this is a complex sinusoid. And we'll use this on the next slide. Okay, so this we can also say x of n by the Euler formula, we can say is 1 over 2 pi times cosine omega naught n minus, because of the minus n up there, j sine omega naught n. Okay, so we have a complex signal in this case that we get out if we just have a spike on one side. Okay, so this result we just got here, we can use to get another Fourier transform pair. These are not really pairs, right? This is just me shifting around the previous answer. But we'll use this answer here to look at sines and cosines. So from basic math, if you go and look at your math identities, how sine and cosine are defined, we would say that cosine of omega naught n is equal to 1/2 times the sum of two exponentials e to the j omega naught n plus e to the minus j omega naught n. And I'm sure you remember that the sign is very similar, but the two differences are that there's a j here on the bottom, so it's complex, and j omega naught n, and then there's a minus sign. That's the other difference, e to the minus j omega naught n. Okay, so these are sine and cosine in terms of complex exponentials, but on the last slide we figured out the link between a complex exponential and what it looked like in the frequency domain. And so you can put those two things together, and what you say is, and you can kind of like just stare at it a little bit, that we can say cosine of omega naught n is going to transform, if we just take this thing and plug in what we had before, it's going to transform to 2 pi over 2. The 2 pi comes from the last slide, the 1/2 comes from this slide. Of course they cancel. Delta omega minus omega naught plus delta omega plus omega naught. Okay, and then the sine of omega naught n goes back and forth. We get 2 pi from the last slide, 2j from here, and of course the 2's will again cancel. Delta omega minus omega naught minus, because of that, delta omega plus omega naught. Okay. So if you look at those, the cosine basically is going to look something like this. In the frequency domain, it's going to be an even function. So we'll get 2 spikes at omega naught and minus omega naught, and they will have amplitude pi. And then for the sine, what that is going to look like in the frequency domain is, it's going to be, again, 2 spikes, but now the sign is different. So we're going to get something here at omega naught, something going down at minus omega naught. And the amplitude here is going to be pi over j, and the answer here is going to be minus pi over j. Okay, so yeah, so this is something we'll use a lot, cosine and sine. So as we increase the frequency of a sinusoid, we'll have this spike here and this spike here. They'll move out, they'll move that direction away from the origin as the frequency gets bigger. And the difference between the sine and the cosine is that one is kind of flipped, and then one's imaginary. The sine is imaginary. Okay, now we come to what is probably the most useful transform pair, which is the boxcar or rectangle to sync, or if you're going the other direction, sync to boxcar pair. So let's say that we have a signal and frequency that looks like this. So here's x of omega, and it is basically flat. It's 1 from some frequency omega c up to omega c. And I should mention the DTFT is 2 pi periodic, so remember, if I kept drawing out, I would have another copy of this centered around 2 pi, 4 pi, 6 pi, minus 2 pi, etc., etc. I'm kind of not drawing that. But this is our, let's say we have this thing. This is called a boxcar because I think it's supposed to look like if you have a a boxcar sitting on a train, they're kind of long rectangles, so that's where that name comes from. Okay, so if you write down the equation for that, you say x of omega is equal to two different things. It's equal to 1 or 0, right? Kind of simple. So 1 if the absolute value of omega is less than omega c, so anywhere in here, and 0 else, 0 otherwise. So this, what we can do is we can just plug that into, this is our boxcar and frequency, we just want to plug it into the Fourier transform equation and see what we get. And in this case, it's kind of worth, at least in a video, going through the details. So if we write down that formula, we'd say we have an integral from minus pi to pi, x of omega, e to the j omega n d omega. I'm just copying things down. But now we can say, okay, x of omega here, and sometimes, by the way, I write this with the top and bottom closed off. I'll do it here just to be consistent. Sometimes I don't. But capital X, it's 1 in this region, 0 else, so we can rewrite this as 1 over 2 pi minus omega c up to omega c, and then it's 1 in there, e to the j omega n d omega. Okay, and then you do the integral, so we have this constant of 1 over 2 pi we're carrying along. And then the integral of the exponential is e to the j omega n over jn. For calculus, evaluated omega c to minus omega c. So we can plug this in, and we can say that is 1 over pi n, 1 over 2j. I'm just reorganizing these things. Then I get e to the j omega c n minus e to the minus j omega c n. The reason I rewrote these is because when you look at this, you'll probably see that this thing here is the definition of the sine, right? So that is equal to, this whole thing is 1 over pi n sine omega c n. Okay, we have a little bit of a problem now. I'll put parentheses there, because this is fine if n is not 0, but if we plug in n equals 0, this goes to 0, so that'll go to infinity, but then the top sine of 0 is 0, so we have the 0 over 0 problem. So we can use L'Hopital's rule to deal with that, and basically what we get is that x of omega is equal to, we have to handle the two cases, so it's sine omega c n over n pi, and not equal to 0, and it's omega c over pi at n equals 0. And the way you can do that last one, you could actually just plug that into the equation. So if we got x of 0, n equals 0, it'd be 1 over 2 pi. It turns out to be just d omega minus omega c to omega c. And if you go through this, this is what you get. Okay, so the pair then, if we draw it out, we started with something that looks like this. Oh, I'm sorry, this is wrong. That is x of n. Right, we start with x of omega, and we get x of n. Okay, so here we have omega, x of omega, minus omega c to omega c. It's 1. And that transforms back and forth, because once we know, one direction, the answer, if we go the other direction, is going to be, they're pairs. It's going to be something that's a sine wave that decays as we go out in n. So this is n, this is x of n. So if we look out, we have the sine wave, but as n gets bigger, it gets divided by something bigger and bigger, so it kind of falls off as we go away. The thing we can figure out is what is this point? Okay, this point being the first 0. Let me give myself a little room. The first 0 here, this is the point where the top here goes to 0, and it's when sine omega Cn is equal to sine of pi, because the first place it goes to 0 is here, but then we had that funny case. So it's sine of pi. So what that says is that it's at n equal to pi over omega c. So what this means is if we spread out, if omega c gets bigger, so if we have something that has more and more frequencies contained in it, what happens over here is this main lobe, the distance between these two zeros, we'll call this the main lobe, this region in here, is going to get smaller because as omega c gets big, the end where this goes to 0 shrinks in and this thing will get smaller. So this is the trade-off between if we're wider over here, we're narrower over here. Okay. The same thing, that was frequency to time, but you can also do time to frequency. This is an example from the book, and I'll let you look at the book. And basically what you get is that if you have a boxcar or rectangle in time, here they're actually doing it for the continuous time Fourier transform, basically the same story over there. You'll get, again, a sink. As the sink gets wider in time, it gets skinnier in frequency. And the other thing you can see is if we were to go to the limit of this thing becoming a delta function, we'll go to the limit of this thing being really, really broad. And we saw at the beginning a delta function will transform to a straight line. Now here, by showing you a picture that is continuous time and continuous frequency, I'm kind of playing a little bit fast and loose, because before I was always doing n and omega, but the fact is that all of these pairs basically work for all of the various Fourier transforms, although the important difference being that the DTFT is 2 pi periodic. So that's the thing we have to keep in mind. All right, the last one I want to do, and the book goes through the derivation, is the pair between a pulse train in time. What does that give us? So if we have a function like this, we can say x of n is the sum of a bunch of different delta functions at different delays. So the idea is we have every m samples, big M, we have a new spike. So here, for example, we might have a spike at 0, at 32, 64, etc. So we have all these spikes going on. What does that give us? And it works out, if you look in the book and go through the derivation, which is straightforward, but there's some steps to it, that in frequency you also get a bunch of spikes. So we get a pulse train there, but things there are spaced by some amount omega sub m, where omega sub m is 2 pi over m. So if we have a big spacing between our samples in time, non-zero samples in time, we'll have a small sampling in frequency, very dense in frequency. On the other hand, if we have a short spacing in time, so we have the thing going to 1 fairly frequently, we'll have a much more spread out sampling in frequency. This is kind of the same kind of picture as before, where when things are getting spread apart in one domain, they're getting closer together in the other. And this turns out to be really the key to understanding sampling theory, which we will talk about separately. The last thing I'll just point out is that I put all the code on Trunk for examples I'll show you in class. You can download them, play with them, and you'll be able to see pulse trains, boxcars, and times and frequency, and so on, and get a feel for how things change as you vary the parameters. I encourage you to do that.